I'm about to teach you the good news about optimization, a 5-step procedure, which is a little easier than a 7-step procedure, right? Okay, so I'm going to teach you a 5-step procedure for solving what are called optimization problems. Okay, now what do you think the word optimization means, or the word optimum? Best, maximum, efficiency. Yes. Okay, now maximum is an optimum, but there's another kind of optimum. There's a minimum. That's right. Optimum is a word kind of like extrema. Extrema means either a maximum or a minimum. Optimize means to make highest or lowest. And it depends on what it is. You want to maximize your revenue in a business, and you want to minimize your expenses, your costs. That's right. Okay? So, optimization is the idea of identifying the best highest or lower number, or highest or lowest number, or let's just say the best number for in making a decision or in some sort of situation. In optimization, we are considering lots of parameters. But here's what we do. We take all the parameters. You guys with us? You guys with us? All right, we take all the parameters and we ball them up into a single function. And then we optimize. All right, so let me draw a graph here. And we're gonna bring the conversation down a little bit, okay? We've been very abstract for the past 5 or 7 minutes. Let's bring it, and this is still abstract, but it's a little more concrete for learning. Okay, let's say that we have a function that does this, okay? Okay, it does that. Now, the idea of optimization is related to the idea of relative minimums and relative maximums. Can you all look up at this graph that I've just drawn and think to yourself, don't shout it out, but think to yourself, how many relative maximums are there? How many relative minimums are there? Okay. Now somebody say it out loud. How many relative maximums? 2 relative maximums, right? One of them's right here and one of them's right here, right? How about relative minimums? There's 2 of them, right? There's one here and there's one here, okay? Well, when you are optimizing, you are looking for maximums and minimums. But more specifically, in an optimization problem, you are looking for, do you remember how last semester when we did this, we were looking for the relative maximums and the relative minimums? Okay, are we okay here? I don't know if you're in the same room as me. I can see you here, but I'm not sure if you're actually here. Okay, you got to be here to hear this. In optimization, we are not dealing with relative maximums and minimums. We are dealing with, yes, but we're going to call them, we are looking for the absolute maximum and the absolute minimum. So, an optimization problem goes one step further than a relative maximum, relative minimum problem. It's not just looking for where the change is in direction. It is looking for the highest point and the lowest point on the graph. Are we good? Okay, so here's the problem with that. Okay, well, it's not a problem. One difference between an optimization problem and what we did last semester with relative minimums and maximums is optimization problems, we're usually looking for an absolute maximum and an absolute minimum on what is called a closed interval, which means this: we have to block off a part of the graph into just one section. We need a closed interval. Now, last semester intervals looked like this. Let's say we have an interval from -3 to 5. Okay, we could have -3 to 5. Do you guys remember this? interval, right? Now, this is an open interval. The reason it's an open interval is because an open interval does not include its... Do you know what these are called? I don't know if I referred to them last semester. There's a special name for the numbers that start and end the interval. Okay? They're called endpoints. Okay, so this, that, and that, those are called endpoints. Okay? In an open interval, the endpoints are not included. Right? See this? It doesn't say greater than or equal to. It doesn't say less than or equal to.
So that's
understand? This is this is an open interval. Okay, this is an open interval. And we could also write an open interval like this. One of the reasons why I like to use this notation with open intervals is because this notation with the parentheses looks like a coordinate. But this is not a coordinate. This is an open interval. X value starting at -3 and ending at 5. Right? We good so far? Anybody want to stop me? Ask me? Yes, go ahead.
Okay. So you're saying for optimization, we're doing closed intervals?
Yes, that's what I'm about to put on. Yep. So, it's not that we have to do closed intervals. It's that closed intervals, there is a theorem. Okay? Do you guys know what a theorem... I've mentioned the word theorem before, right? In math, the word theorem means the same thing as something else in science. Do you guys know what word is used in science that means the same thing as theorem? What's that? Not hypothesis, better than a hypothesis. Stronger than a hypothesis. Okay, what's stronger than a theory? When something starts out as a theory and then that's right. And it receives absolute, complete support in every circumstance. It's called a law. A theorem in math is a law in science. A theorem is a situation where it's always true. There is never a time when it's not true. If it has been deductively, absolutely proven mathematically to be true every time, we call it a theorem. Now, there is a theorem in calculus. Okay, there's actually 5 theorems, but I haven't really taught them to you because it seems like every year, whenever I teach the theorems, everybody's eyes start to glaze over, their brains get twisted up, and then they forget all of their calculus because of the theorem. So I just decided, I'm not going to teach the theorems directly. I'll teach them indirectly, right? However, anyone taking the AP exam is going to need to know these theorems. So who in here, just informally, anybody interested in taking the AP exam? Okay, all right. Interested, okay, so about half of you guys. You guys, we're going to have to meet separately or I'm going to have to make a video where I explain the theorems to you, okay? But I'm going to explain one of them right now, but only for conversation. We're only doing this for conversation. Don't write this down right now, okay? For conversation, for kind of understanding this. There is a theorem in math that says this. If you have some function on a closed interval, has to be on a closed interval, and that function is continuous on the closed interval. Continuous meaning it doesn't have any holes. Remember that? Holes, right? Doesn't have any vertical asymptotes. Remember vertical infinite discontinuities, right? Doesn't have any vertical asymptotes. Doesn't have any jumps, right? Do you remember when we did continuity? Jumps, holes, and infinite and vertical asymptotes, they were the reason that a function would not be continuous. So as long as the function doesn't have any of those 3 things on a closed interval, then that function on that closed interval will have one maximum, one absolute maximum, and one absolute minimum. One. Does that make sense? Okay? All right. The theorem falls apart if it's an open interval. See, if it's an open interval or if it's not continuous, then you can have a place where it keeps reaching but never getting to the maximum point or the minimum point. Okay? I'll show you let me show you an example in about 5 minutes after I make a point here. Okay, everybody, stop what you're doing, look up at this graph. I want you to think to yourself for about 10 seconds, 15 seconds, and then we'll say it. Where is the absolute max? Oh, you know what? I forgot to write. Hang on, I forgot to write the closed interval. If this is a closed interval, it'll look like this. -3 less than or equal to x less than or equal to 5. Or x is between -3 and 5, including -3 and 5. Do you see that? Yes. Say again? Yes. That's correct. That's exactly right.
So
Yep.
it's open because it kind of leaves the possibility that there's numbers beyond.
Well, there are. I mean, let me ask you something. What is the first number in this interval? Nope. Well, actually, it's on the other side. It's -2 because this is a negative, right? So it's -2.99999. Can you finish that up for me? That number? You understand? Do you understand that if you wrote down that number and you wrote it until the day you died, and then when you died, you bequeathed that task to your son or daughter, and they kept writing the 9, and then they bequeathed that task to their son or daughter, and it went on for 10 or 12 generations, even more generations, right? That they would still never be done writing that number. Does that make sense? Therefore, we cannot nail down that number. We know it exists. We know it's right next to -3. But because we cannot explicitly identify the number, it can't be called a maximum or minimum. Does that, or we can't call it the beginning or the end. Sorry, we'll get to the maximum minimum in a minute. We can't call it the beginning of the interval. So the only way that you can actually write down that that is the beginning number is instead you say, well, it's greater than -3. It's all the numbers greater than -3, but don't include -3. Now we are implying that we wrote the number down without actually having to write the number down because we can't write the number down. Does that make sense? I know it's a mind bender talking about it that way, but that's basically the idea. Okay? So the way that we include that number without having to write it down over 15, 20 generations is we write x is greater than -3. Okay? Similarly here, what is the last number in this interval? 4.999999999999999, and for hundreds of generations your children write down 999999999 and fill up all the paper in the universe and fill up all the space in the universe and write 9s on all the beaches in the universe. See what I mean? It would go on forever. It's an infinite number of 9s. Therefore, we can't write it down. Therefore, in order to write it down, instead we just say less than 5. The next number that is up to the next number less than 5, which we can't write down. Are you guys okay? Okay. Those of you that are stronger abstract thinkers understood that better than those of you that are weaker abstract thinkers. Yes. And that's okay.
The word you said earlier was bequeath.
Yes. Is that the correct word? I think that's the right word. Yeah. You know, like it's like you are heiring something to some. You know, they're inheriting it. Yeah. Okay. It might not be the right word. I don't know. I'm not. Yeah. But I think it's the right word. Yeah. We should look. Somebody should look that up. Bequeath. Bequeath. I think. Okay. All right. So now, the way we would write closed interval like this would look the same. -3 to 5, except what? That's right. Use brackets or, yeah, there you go. Boxes is good too. That's fine. Use brackets, okay?
So the top one is open?
Open interval, closed interval. Yep. So what we have here, this means starting at -3 and ending at 5, inclusive, meaning include -3 and include -5. Now, the beginning of this interval is -3 and the end of the interval is 5. Okay? And because we are concrete on those numbers can be the maximum or the minimum. Okay? So, looking at this graph, everybody see if you can figure out, think to yourself, where is the absolute maximum point on this interval, closed interval, and where is the absolute minimum point? Take 10 seconds, don't say it out loud. Okay, now before you say it out loud, here's what I want to tell you. Is that there are 6 possibilities. 6 possible points that could be the absolute maximum or absolute minimum. Okay? The first possibility is this endpoint, A. The second possibility is this low point, which we understand as a relative minimum. All relative maximums and minimums are possible absolute maximums and minimums. So we're going to say that this is the second possibility. Here's our third possibility. Here's our fourth possibility. Here's our fifth possibility. And our fifth possibility is the endpoint on the other side. Now, where do you think the absolute maximum is? Is at point A. It is the highest point, highest output value of the whole graph on the closed interval, right? Any questions about that? A is the absolute maximum. Where is the absolute minimum? It's at B. This is the absolute lowest point. This endpoint over here is low, but it's not that low. This point right here has the lowest output value on this closed interval. We're swimming in the pool of calculus. Is anybody drowning right now? Does anybody need a lifeguard? You guys okay? If you're floating, that's good. If you're floating, that's okay. I'm okay with floating. Swimming is better. Floating is okay. Drowning is not good. Is anybody splashing around starting to lose their buoyancy? No. That's not good. If you're dead, we gotta call the paramedics. Yeah. All right. How are we doing? What's that? Yeah, Chaz is the lifeguard. Yes. Band-Aid? Did you say Band-Aid? Yeah. 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 Can you hand this behind you? Can you hand this the other direction behind you? Okay. All right. So now, how are we? Yeah. Oh, down the hall? Oh yeah, just duck. Okay. So here we go. So we have the absolute maximum and we have the absolute minimum. Are we okay so far? Okay, so here is what I'm going to show you how to do. I'm going to show you how to do exactly what we just did, only without a graph. See, it's easy to see the absolute maximum and absolute minimum on a graph, but what happens when you're given an analytic function and you have to find the absolute maximum and the absolute minimum, okay? Are you guys, we're tied in? Okay, let me ask you this. When we were learning about relative maximums and relative minimums, how did we find those things? Do you guys remember how we did that? How did we identify that B, C, D, and E? How did we find those points? Zeros of what? What did you say? The critical values. And the critical values, those are the X values for these points, are the critical values, right? And how do we find the critical values? The zeros of the derivative. Do you remember that? Or are you now remembering that? Okay, that the critical value. So here's the thing. You have to remember this phrase, critical values. It's going to, excuse me, that's veil. Sorry. Critical values. You have to know how to find critical values. You were tested on that. That was on the final exam. Remember? We did that a good bit. You have to know how to identify the critical values of a function in order to be able to identify the possibilities for the absolute maximum and the absolute minimum. Okay? All right, let's do it. I'm going to erase all this. Can I erase all this? Any questions? Closed interval, open interval, a function on a closed interval. It's continuous in the middle. We're about to do critical values. Good. All right. Now that we've got our vocabulary and the concept going on, I am now going to give you a 5-step procedure. Really, it's 4 steps. The 5th step is the write your answer down step. Okay, so it's more 4 steps than 5 steps, but let's go ahead with it. I have it over here because I taught it the other day. Okay. Step 1. So you're given a function on a closed interval, and the question says, what is the absolute maximum and what is the absolute minimum of this function on this closed interval? Step 1, the very first thing that you're going to do is you are going to find the derivative and set it equal to 0. Find the derivative and set it equal to 0. Why? Why are we going to find the derivative and set it equal to 0? Yes, because it's the slope, but more specifically about the slope. What did you say?
So you'll know the critical value.
Because the critical values are the zeros of the derivative. And that's what we need. What we're looking for here, it's our goal, is to find all of the possibilities for absolute maximum and absolute minimum. And we know that the absolute maximum and absolute minimum could be occurring at relative maximums and relative minimums, which occur at critical values, which we find by setting the derivative equal to 0 and solving for x, right? Okay, so step 1, you're going to find the derivative, set it equal to 0. Step 2, identify the critical values, which basically means solve this equation. Find the zeros of the derivative. Identify the critical values. That's the second step. Okay? These are the zeros of the derivative. Zeros of the derivative. Okay? See, technically, step 1 and step 2 are the same step. I could have just said, find the critical values of the function, right? Which means find the derivative and set it equal to 0. But I also know that for you guys, you want your steps to be clear, okay? And the first part of that is going to be finding the derivative, setting it equal to 0. Then find the zeros and list them. So for step 2, it would be x equals this number, x equals this number, x equals this number, whatever. Okay? We doing okay so far? All right, good. All right. Step 3. Now, steps 3 and 4 kind of go together. Okay, but I do step 3 first and then I do step 4. And let me explain how I usually do steps 3 and 4. I usually create a table of values. You know, you guys remember making T tables when you were in maybe 6th or 7th grade? Your teacher would give you a function, you'd have a T chart, you'd have the X's, you'd have the Y, you have Y here, you'd have a function, you plug all the X's in. What's that? Well, in here? Well, yeah, but what I mean though is this, is I'm recalling back, I'm reminding you that you have probably been doing it in lots of math classes for the past 5 or 6 years, right? So I'm making the concept less intimidating. I'm trying to make the concept less intimidating by telling you this is not something new to you, right? Okay, so step 3 is you are going to identify all X value candidates. Identify all X value candidates. What is a candidate? What does the word candidate mean? Yeah. Possible winner, right? Okay? A possibility. When we vote for someone possibly going into office, we have candidates, and then we vote on the candidates, and one of them presumably will be the winner, right? Okay, so what's going on here is when we say candidates, this is a word used by the AP Calculus exam people, okay, the College Board folks for AP Calculus. When you read some of the solutions to some of the AP exam questions, it'll say something like, oh, they get 1 point for identifying x equals 3 as a candidate, as a possibility for absolute maximum, absolute minimum, okay? And there's two kinds of candidates. Two kinds of candidates. The critical values are all candidates, which you already identified in step 2, right? You've identified some of the candidates in step 2. And now, does anybody remember what I said? Where else can the maximum and minimum occur? At the endpoint. So all of the candidates are the critical values and the endpoints.
That's it?
Yeah, that's it. Those are all your candidates. So I usually start with my left endpoint, then I write down all my critical values, then I put my right endpoint. And then now I have all of my candidates. Okay? Step 4, you gotta be careful on step 4. Step 4, plug all candidates. Plug all candidates into. Now, please remember this. I'm going to emphasize it by using all caps. Okay? Plug all candidates into the original function. I'm also going to throw an underline in there. Okay? You're going to plug all the candidates into the original function. Do you know why you're going to plug them into the original function? Because we are looking for the maximum and minimum of the original function. We don't want the maximum and minimum of the derivative, but what a lot of people do is they'll plug the candidates into the derivative, which is really weird to me, because what do you think they will get as an output value when they plug all the critical values into the derivative? They should be getting 0, right? So you should have a bunch of zeros there. That should be your first clue that you did something wrong. Not that you can't get 0. That happens sometimes. But that you shouldn't get a whole bunch of zeros, probably. Okay? Although I could think of a question about 30 seconds that would give you 0 as all your output values. It would drive you crazy, but I'm not going to do that. Yeah. Sine of x minus 1. All your maximums will be at 0. Think sine of x, right? Sine of x has a maximum of 1 and it has an infinite number of them, right? So then we just go minus 1. Now all your maximums are 0. Or sine of x plus 1 would give you all your minimums would be. Sorry, I'm just having fun. I'm just showing off right now. Okay. Plug all your candidates into the original function. And so here, this is what I usually do. I turn this into a table of values. And what I'll do is this. I usually do it sideways. And what I'll do is on the top, I'll have all the x values. And on the bottom of the table, I'll have all the output values. Okay? And then step 5, the final step, is pick the smallest output value, pick the smallest output value as the absolute minimum and the largest output value as the absolute maximum. And you're done. So basically, you're looking at your list. You have all your candidates, you have all your x values, you've plugged them all into the function, so you have all the output values at those x values. Of all those output values, whichever one is the largest number is the absolute maximum of that function on that closed interval. Whichever of those numbers is the smallest number is the absolute minimum of that function on that closed interval. Are we still afloat in the swimming pool of calculus?
So we're gonna do number one now?
We're going to do number one right now.